Introduction. Sulfur hexafluoride, SF6, has been used as an insulating medium in switchgear industries since the latter half of the last century. Its application has been extended to other areas of electrical products where there was a need to make them more compact, taking advantage of the much superior dielectric properties of this gas. This was partially driven by the need to install high-voltage substations comprising gas-insulated switchgear in urban load centers where there was a constraint on the availability of land. The use of this technology for the transmission of bulk power over longer distances was a logical extension and resulted in the development of gas-insulated bus, GIB, also referred to as gas-insulated lines, GIL, or gas-insulated transmission lines, GITL. In a gas-insulated switchgear, SF6 not only provides the desired insulation but also facilitates the quenching of arc triggered by braking, switching, or earthing devices. In the gas-insulated bus, it provides only the necessary insulation. The volume of gas required in a substation comprising gas-insulated switchgear is far less than the volume of gas required in a gas-insulated bus of any significant length. Consequently, the cost of gas as a percentage of the cost of equipment is far higher in gas-insulated bus when compared to that of a gas-insulated switchgear. Since sulfur hexafluoride has been identified as a greenhouse gas, efforts are on to reduce its usage and find alternatives. A gas-insulated bus with a mixture of 80% nitrogen and 20% sulfur hexafluoride is considered as an environmentally friendly option. It is often referred to as second-generation gas-insulated bus. This reduces the cost substantially for long-distance bulk power transmission. Further dielectric gas, green gas for grid G3, with low global warming potential, GWP, and higher dielectric strength have been developed and used in gas-insulated bus. It is notable that a well-designed and operated gas-insulated bus system achieves essentially zero emissions of sulfur hexafluoride and consequently no significant global warming impact. Alternate options to sulfur hexafluoride gas offer challenging design constraints for practical implementation under certain ambient conditions such as in outdoor installations where the temperatures are below -25 degrees Celsius, -13 degrees Fahrenheit. With the increase in the system voltage for substation rising to 1200 kV and the need to protect it from the vagaries of nature and environmental conditions, by installing them indoors, gas-insulated switchgear has found acceptance even where the land was not at a premium. Gas-insulated bus, also called gas-insulated transmission lines, was a natural extension of this idea. Gas-insulated bus have been manufactured and installed up to a rated voltage of 1200 kV and rated current of 8000 amperes. In 1975, the very first gas-insulated bus rated for 400 kV was installed in a pumped storage plant in Schlucksee, Germany. Table 13.1 details the compactness ratio for different system voltages. The compactness becomes more evident with the increase in the system voltage. Gas-insulated bus can be installed in a horizontal or vertical configuration and run overhead or underground, in trenches or tunnels, or directly buried. These are not expected to be opened, inspected, and maintained for the life of the equipment. Gas-insulated bus is not inflammable and is not a fire hazard. Gas-insulated bus also have a very high electromagnetic compatibility, EMC. The magnetic field, measured as flux density in microtesla, under similar measurements, is significantly lower than that of a cable or an overhead line operating at the same voltage and current. The corona loss in a gas-insulated bus is lower than that of a cable or overhead line for a similar application. A very high degree of reliability is expected of gas-insulated buses. The reliability of the support insulators, contamination of metallic particles, and susceptibility to very fast transient overvoltage, VFTO, generated by the operation of disconnector switches are inherent in the design of the gas-insulated bus and therefore needs careful consideration. The requirement of GIBs have been mainly felt in the following locations: line crossings, vertical shafts, transmission line, upgradations. Line crossing. There may be situations where due to line congestion, it may not be possible to lay an additional high-voltage connection to the existing switchyard or connect a new line for power evacuation during the expansion of a power plant, that results in the crossing of the existing lines. Air-insulated conductor systems with the desired air clearances do not offer a solution. Such connections are best carried out by a gas-insulated bus that is either run overhead or underground. Vertical shaft. In several large hydroelectric plants, the generators are located underground. The power is evacuated from the generator transformer through high-voltage transmission lines. There are two options for locating the generator transformer. The generator transformer could be located over the ground and the transmission line can be connected to its HV terminals. The connection between the generator terminals and the LV terminals of the generator transformer will be through an isolated phase bus carrying a large magnitude of current at medium voltage. The isolated phase bus will run through the vertical shaft. The cross-section of the shaft has to be large to accommodate the isolated phase bus and space for routine maintenance and evacuation of heat generated by the isolated phase bus. The generator transformer can be located underground close to the terminals of the generator, and a gas-insulated bus carrying a smaller magnitude of current at high voltage can be run through the vertical shaft and connected to the transmission line. The gas-insulated bus generates fewer heat losses, does not require maintenance, and the cross-section area of the shaft will be less. Gas-insulated bus will weigh far less than an isolated phase bus for carrying the same power for obvious reasons. A hydroelectric power station has a vertical gas-insulated bus of 300 meters, 1,000 feet, suspended from the top. A techno-commercial analysis can establish the selection of any one of the two alternatives. Transmission line. Gas-insulated bus can be run in any of the following modes. Above ground. Gas-insulated bus can be run above ground, at a convenient height, supported on the structure. This mode is preferred when transmitting large power over long distances. In tunnels and trenches. Gas-insulated bus can be run below the ground in prefabricated tunnels and trenches. It is also run in trenches when there are road crossings. The gas-insulated bus can be run horizontally, 3 phases side by side, in trenches, and vertically, 3 phases one above the other, in tunnels. Gas-insulated bus are also run on the sidewalls of tunnels meant for transportation by rail or road. Buried underground. Gas-insulated bus is buried horizontally at a depth determined by the terrain and soil conditions. This is the most economical way of running a gas-insulated bus. The enclosure needs to be protected against corrosion. Once the GIB is installed, the landscape can be brought to the original conditions. Upgradation. Gas-insulated buses are also required when undertaking retrofitting, modification of an existing layout, and addition of bays to existing substations. It does offer a solution that would not have been possible with an air-insulated system. Description. The gas-insulated bus mainly comprises a cylindrical conductor or conductors located inside a cylindrical enclosure and supported by insulators. The annular space between the conductor and enclosure is filled with insulating gas. Sulfur hexafluoride. A mix of sulfur hexafluoride and nitrogen in the ratio of 20:80. Green gas for grid. There are 2 possible configurations for a GIB detailed below. 3-phase gas-insulated buses have been installed for short lengths, at lower system voltages, when they are coupled to a 3-phase GIS unit. Since the phase spacing is minimal and the conductors do not have a shield, the short circuit forces will be far more severe in a 3-phase configuration than in a single-phase configuration. The enclosure losses will be far less in a 3-phase configuration than in a single-phase configuration for the same rating. Single-phase gas-insulated buses are more practical for the following reasons. Ease of manufacture. The electric field is radial and symmetrical if not uniform. It makes modeling and analysis easy. It is a very important criterion when designing a gas-insulated bus for high voltage, extra high voltage, and ultra high voltage systems. It eliminates phase-to-phase faults. The short circuit forces will be negligible not only because of larger phase spacing but because of the minimum flux design. The insulator span can be large, reducing the number of support insulators. Each insulator location is a potential cause of failure. For long route lengths, a spare single-phase GIB can be installed as a standby, for more than one set, in the event of an outage on any one of the phases. The gas-insulated bus can be classified under the 2 following categories. An active gas-insulated bus that has a disconnecting and grounding switch in the gas compartment. A passive gas-insulated bus that does not have any moving or switching device in the same gas compartment. The main components of a GIB are enclosure, enclosure support, conductor, conductor support, insulator or bushing, insulating gas. In addition to these, there are several accessories, comprising telescopic finger contact assembly, compensators, isolating device, particle traps, terminations, lightning arresters, protection against corrosion, cathodic protection, for buried GIBs. Mr. Balachandran graduated with a bachelor's degree, B.Tech, in electrical engineering from the Indian Institute of Technology, Madras, India, in 1967, and obtained a master's degree, M.E., in power engineering from the Indian Institute of Science, Bangalore, India, in 1970. He is a Fellow of the Institution of Engineers, FIE-India, Fellow of Institution of Engineering Technology and Chartered Engineer, FIET-UK, and Life Senior Member of the Institution of Electrical and Electronics Engineers, IEEE-US. He was the founder-director of Power Gear Limited and Busbar Systems, India, Limited. He has worked in manufacturing industries in India and the UK and is currently an advisor. He has engineered several busbar systems that have been manufactured and installed in various countries, including isolated phase bus for the largest hydroelectric power plant, 26 by 800 megawatts, at the Three Gorges project in China. During his professional career, he has developed and tested a range of bus products and their accessories. His area of interest also includes switchgear, instrument transformers, and power system analysis. The book, An Introduction to Busbar Systems, authored by V. Balachandran, is case-bound, hardcover, size A4, 386 pages, printed on 100 GSM glossy paper. Copies of the book can be purchased with a requisition to Bala at busbarsystems.net. Black and white version of the book is for sale in India, Afghanistan, Bangladesh, Bhutan, Nepal, Pakistan, and Sri Lanka at a cost of 4,500 Indian rupees plus freight. Color version of the book is for sale in all other countries at a cost of US $126.00 plus freight.